same company. How could this happen? We are the best intelligence organization in space. How could we miss that? I have to inform the Big Yahoo. Quickly, inform Space Tel Aviv.
And the few new guns they added to the game, guns and additions that could as well have been a mod, or to play the bonus missions that kind of also feel like they are
bonus missions. The bonus missions. The bonus missions. The bonus missions.
We'll go over ways to take the derivative of combinations of functions. The first is the addition rule. It says that the derivative of the sum of two functions is the sum of their
Check one, check. Oh, say, can you see by the dawn's early light what so proudly we hailed, and the twilight as whose broad stripes and bright stars through the perilous fight for the ramparts we watched were so gallantly streaming, and the rockets red glare, the bombs bursting in air gave proof through the night that a flag was still there. Oh, say the star-spangled for the land of the free and the home of the brave. Thank you. Appreciate it. Thank you. You're too kind. And the home of the brave. Everybody wants to move. Say that you never need it. No hairline, why believe it?
distinct derivatives. Or, in terms easy to remember, the derivative of the sum is the sum of the derivatives. Here I'm using
The derivative of the sum is the
f and g as the two functions and the prime symbol to denote their derivatives. An example should make this simple. Let's find the derivative of x squared plus x. First, the derivative of x squared is 2x, and the derivative of x is 1. So the derivative of x squared plus x is 2x plus 1. The derivative of the sum equals the sum of the derivatives. Let's look at the graph and see why this makes sense. Here are the two functions we're adding, y equals x squared in white and y equals x in green. And the blue curve is their sum, y equals x squared plus x. Let's take two nearby x values and look at the corresponding delta y's for the three curves. Here's delta y for white, the change in x squared over our small delta x. And here's delta y for green, the change in green y over our small delta x. And finally, here's delta y for blue, the change in x squared plus x over our small delta x. Can you see that since blue equals white plus green, that delta y for blue equals the sum of the white and green delta y's? Since blue equals white plus green everywhere, any difference in blue must be equal to the corresponding difference in white plus green. Remember, as delta x approaches 0, we use the word differential to describe the changes. So the differential of the sum equals the sum of the differentials, and that's the addition rule. Without elaboration, I'll assert that the same relationship holds with subtraction, that the derivative of the difference between two functions equals the difference of their respective derivatives. So I'll write the addition rule with plus or minus, since it works for addition and subtraction. Next is the product or multiplication rule. It says that the derivative of the product of two functions is the first function times the derivative of the second, plus the second times the derivative of the first. So I'll write the addition rule with plus or minus, since it works for addition and subtraction. Next is the product or multiplication rule. It says that the derivative of the product of two functions is the first function times the derivative of the second, plus the second times the derivative of the first. So the pattern is different than the addition rule, because the derivative of the product is not the product of the derivatives. Since it works for addition and subtraction. Next is the product or multiplication rule. It says that the derivative of the product of two functions is the first function times the derivative of the second, plus the second times the derivative of the first. So the pattern is different than the addition rule, because the derivative of the product is not the product of the derivatives. Like we did for the power rule, let's visualize the product rule by considering the product of the two functions to be a rectangle whose area is the product, f times g. On this graph, the axes represent the values of the functions, not the independent variable x, at least not directly. When we increment x by its differential dx, f of x increases by its own derivative, df by dx, and the area of the rectangle increases slightly by this thin strip. the same time, g of x increases by its own different derivative, dg by dx, and the area of the rectangle increases slightly by this thin strip. The area of this first strip is its height, g of x, times its width, df by dx. And the area of the second strip is its height, dg by dx, times its width, f of x. So the derivative of the product of the two functions is the additional area of the two rectangular strips, and their dimensions are each function times the derivative of the other, and that's a nice visual interpretation of the product rule. Now we can look back at our sample function x squared minus 2x plus 1 and consider which of these rules we'll need to use to find its derivative. Well, it's the sum of three simpler functions, so let's start with the addition rule. The derivative of x squared is 2x by the power rule. For the next term, we need to subtract the derivative of 2x, which is the product of 2 and x. So we'll need the product rule. We'll get back to it in a second. And the derivative of 1 is 0 by the constant rule. Interesting. To take the derivative of a simple polynomial, we need all four of the rules we've covered so far. Now, let's use the product rule to find the derivative of 2x. The product rule says that the derivative of the product is the first function times the derivative of the second plus the second function times the derivative of the first. The first function is 2, and the second function is x. The derivative of 2x is 2 times the derivative of x, plus x times the derivative of 2. The derivative of x with respect to x is 1 by the power rule, so the first term becomes 2 times 1. The derivative of 2, a constant, is 0, so the second term becomes x times 0. This also simplifies to 2. Derivative of x with respect to x is 1 by the power rule, so the first term becomes 2 times 1. The derivative of 2, a constant, is 0. So the second term becomes x times 0. This all simplifies to 2. So the derivative of 2x is 2, which makes the derivative of our original function, x squared minus 2x plus 1, equal 2x minus 2. Of course, this is the The same answer we got when we took the limit. Well, this is the function I promised you'd be able to differentiate in a few seconds, but using these 4 rules certainly took more than a few seconds. Let me show you a calculus super shortcut based on the product rule. The derivative of any constant k times x with respect to x is simply the constant k, because when we use the product rule, we get k times the derivative of x plus x times the derivative of k. The derivative of x with respect to x is always 1, so the first term will always be k. And the derivative of k with respect to x is always 0 by the constant rule, so the second term will always be 0. This pattern occurs every time the product rule is applied to kx, so the derivative of any constant k times x is always k. This is the kind of pattern the rules of differentiation let us exploit. Now, let's go back and find the derivative of x squared minus 2x plus 1 at x equals 1.6 by differentiating left to right. 2x minus 2. With practice, you'll learn to ignore constants. Plug in the chosen x value of 1.6 to get 3.2 minus 2, so 1.2. And that's how, with practice, you can know almost immediately that the derivative or slope of x squared minus product rule. The derivative of any constant k times x with respect to x is simply the constant k, because when we use the product rule, we get k times the derivative of x plus x times the derivative of k. The derivative of x with respect to x is always 1, so the first term will always be k. And the derivative of k with respect to x is always 0 by the constant rule, so the second term will always be 0. This pattern occurs every time the product rule is applied to kx, so the derivative of any constant k times x is always k. This is the kind of pattern the rules of differentiation let us exploit. Now, let's go back and find the derivative of x squared minus 2x plus 1 at x equals 1.6 by differentiating left to right. 2x minus 2. With practice, you'll learn to ignore constants. Plug in the chosen x value of 1.6 to get 3.2 minus 2, so 1.2. And that's how, with practice, you can know almost immediately that the derivative or slope of x squared minus 2x plus 1 at x equals 1.6 is 1.2. Okay, now for another great shortcut, which is a generalization of the first one for kx. This time we'll take the derivative of kx to the n. So we have a power of x with some constant coefficient k. So this is the product of two functions, k and x to the n. Let's use the product rule again and see where this leads us. We have the first times the derivative of the second plus the second times the derivative of the first. The derivative of x to the n is straight from the power rule, n times x to the n minus 1. And the derivative of constant k is, of course, 0. So the second term becomes 0. This leaves the derivative as k times n x but the second term becomes 0. This leaves the derivative as k times n x to the n minus 1. At first, this new shortcut looks a little cumbersome like the power rule did. But look at what it lets us do. When we bring the exponent downstairs, we can just multiply it by whatever coefficient is already there. So the derivative of 4x cubed is 12x squared. We bring the 3 downstairs, multiply it by the coefficient of 4 that's already there to get 12, and then we subtract 1 from the exponent. This simple super shortcut has the product rule, power rule, and constant rule built in. It automatically follows all the rules. So, knowing this super shortcut and using the addition rule, we can easily take the derivative of long polynomials. We just work left to right, differentiating one term at a time. Polynomials are incredibly simple to differentiate. I need to finish the rules of differentiation, but first we actually know enough calculus to solve some interesting problems known as optimization problems. They involve finding the local minimum and maximum values for a function. For example, suppose this curve represents the net profit our company would make by manufacturing and selling X number of a particular item. If we make and sell too few, our profit will be limited by the low number. If we make and sell too many, our supply might exceed the demand, and our extra cost for running more machines and hiring more people won't be offset by the higher volume. There's some independent variable here that will maximize the profit function. How do we find it? Let's notice that at the maximum, the slope of the function is 0. Lucky for us, we know calculus. We can take the derivative of the profit function and find the equation for its slope anywhere. When we set the derivative function equal to 0, we can solve for x to get the exact point at which the original function is at its maximum. Our profit function f of x in thousands of dollars is negative 0.012x squared plus 9.8x minus 1,500, where x is the number of units we manufacture and sell. To find the value for x that maximizes the function, we take the derivative of the function and set it equal to 0 and solve for x. We know how to take the derivative of polynomials. We have negative 0.024x plus 9.8. Set this equal to 0 and solve. X equals 408.3. So we should make 408 units to maximize our profit. If your problem statement asks you for the profit amount, plug 408 into the original profit function to get the maximum profit amount. F of 408 equals 500.8. And we're told this is in thousands of dollars, so the maximum profit is $500,800 when we make and sell 408 units. Let's do another problem. Suppose we have a rectangular sheet of metal that measures 32 centimeters by 24 centimeters. We want to make a box by cutting squares out of the corners and folding the resulting sides out. The box won't have a lid. The shapes we cut out of the corners need to be squares so that when we fold the sides up, they'll all have the same height. What are the dimensions of the box having the greatest volume, and what is the volume? Okay, we need to express the volume V as some function of a variable. Let's use the length of the square sides that we cut out of the corners and call it x. Of course, all of these distances are x. The volume of the box will be its width times its depth times its height. The width is this distance, which in centimeters is 32, minus 2x. The depth is 24, minus 2x. So when we multiply these expressions, that gives us 4x cubed minus 112x squared plus 768x. I'm skimming over the algebra so we can focus on the calculus. To find the x value that maximizes this function, we'll take the derivative, set it equal to 0, and solve for x. The derivative of the polynomial is 12x squared minus 224x plus 768. This is a quadratic equation, and there are several ways to solve it. I used, but won't show, the quadratic formula to get two possible solutions, x equals 14.1 centimeters and x equals 4.53 centimeters. We need to check these numbers for feasibility. The short side of the metal sheet is 24 centimeters, so we can't cut out squares greater than 12 centimeters. There's not enough metal on that edge. So that leaves 4.53 centimeters as our answer for x. But that's not the answer to our problem. We're asked for the dimensions that maximize the box's volume and for that maximum volume. So we plug in 4.53 centimeters for x into our width and depth formulas. We get a width of 22.94 centimeters and the depth of 14.94 centimeters. The third dimension, height, is our value for x, 4.53 centimeters. So multiplying these dimensions yields a volume of 1,552 cubic centimeters. Any other value for the square size x will result in a lower volume. Let's look at a different function. This curve has 2 points where the slope is 0.
I have to go to bed, guys. I had a long day at work, so. And I'm tired, actually, so.